These are the notes on momentum, impulse, and conservation of momentum that are extending into some more challenging problems. So just a quick review, right? Here's an important thing about momentum. Hopefully you already know, right, that momentum is a vector quantity, right, because we were assigning direction with our velocity as far as plus or minus depending on the direction. And we already know, right, the equation for momentum, just a quick reminder, P equals mv, right? Remember that mass has to be in kilograms and velocity is a vector quantity, so assign direction with a negative and positive. So impulse, it says today we use F equals ma as a quick definition of the second law of motion, right? Newton's second law. But Newton did not express it in that form. Instead, he said that a force was the rate of change of momentum instead of F equals ma. Well, basically what happens, right, is here's that equation that Newton came up with, and we've kind of rearranged it since then. We know that A, right, equals the change in velocity over time, and we have Newton's second law, which we're currently using. And so you can see if you substitute in this change in v over t for acceleration, right, we get our change in v over t is here. So F equals m change in v over t. When we move the change in t over to the left, we get F change in t equals m delta v, which is that impulse momentum theorem that we had been using, right? Where F delta t is the impulse that causes the m delta v, that causes that change in momentum. So let's move down. So on the AP test, which of course I know you're not taking right now, but just looking at it, right, they love to do graphs. So we're going to look at a force versus time graph and work through some problems on the graphs. So number one, an estimated force versus time graph for a baseball struck by a bat is shown. From this curve, determine A, the impulse delivered to the ball, and B, the average force exerted by the ball. Well, when something is hit, like a ball's hit, there isn't a constant force. That force varies over time. So this graph represents how at 1 second, at 1 millisecond, the baseball made contact, and that force increased as time went on to a maximum of 18,000 and then decreased, right? And the impact ended at 2.5 seconds. So the total time, of course, is 2.5 minus 1. So the total impact time was 1.5 millisecond. Okay, so what you need to know about these graphs is that the area under the curve is the impulse. Okay, so impulse, right, because impulse is force times time. So if you find the area under the curve, you're taking the force and you're multiplying it by the time. So the area, right, under the curve is our impulse. So looking at the shape here, we have a triangle. So for this particular one, the area under the curve is 1/2 base times height. So solving for that value, right, we have 1/2. Our base is 1.5 milliseconds. I'm just going to say they're seconds just so we don't have to convert it. If you do need to convert milliseconds to seconds, you just move the decimal over 3 to the left. But let's just say it's seconds just to make it easy. So 1.5 seconds, and the height, right, we can see that it's given to us is 18,000. So solving for that, we get 13,500 newtons times seconds. So the impulse, right, that was applied was 13,500 seconds. So part B says, what's the average force exerted on the ball? Well, we know that impulse is force times time. So we know that 13,500 is our impulse, right? We know that the time that force was applied was 1.5 seconds. So on average, the force was 9,000 newtons. Okay, let's look at number 2. What impulse is required to stop a 0.25 kilogram baseball traveling at 52 meters per second? B, if the ball is in the field, if the ball is in the fielder's mitt for 0.1 seconds as it is being stopped, what average force was exerted by the ball? So this is just a quick review of that equation. That remember that impulse is force times time. They're actually giving us, right, the change in momentum, because the change in momentum is mass times change in velocity. So we really could say that if we know the mass times change in velocity, we know the impulse. So impulse equals the mass in kilograms, 0.25, times the change in velocity. It ends at 0, so that's our final velocity, and it started at positive 52, so final minus initial gives us the impulse of negative 13 newtons per second. And moving on to part B, right, now we can find the force if they specifically want to know the force. So force, right, is change in momentum over time. That's that equation that Newton came up with, right? Our change in momentum essentially is the impulse of 13. And we know the time was 0.1 seconds, so we know that the average force was negative 130 newtons. So the graphs are pretty easy, right? The area under the curve, and then just that quick review. So let's move on to the next section. Okay, so glancing collisions. This is a little different than before. Before we had collisions that just happen in the X direction or just in the Y direction, right? And that isn't realistic. Things are going to glance, meaning one object is going to hit another object and cause them to move in directions that aren't just in the X or Y. So in order for that to happen, the thing you need to realize is we know momentum is conserved. Well, momentum is conserved in the X and the Y direction. If all of the momentum is conserved, then it's conserved in the X and Y individually, and we actually have to break it down into the X and Y in order to be able to do these problems. So let's see here. We got a 8 kilogram mass is moving east at 15 meters per second. So we know this is 8 kilograms, right? And it is moving to the east, which is a positive value of 15 meters per second. It strikes a 10 kilogram mass, so that is this one, right? 10 kilogram mass that is at rest, so its initial velocity is 0. The 8 kilogram mass ends up going at 4 meters per second. So we know that this, this 8 kilogram mass is now going at 4 meters per second. And it says south, so we're going to make that a negative value, right? We're going to say that if something is moving to the right, it's positive, to the left, it's negative, up is positive, and down is negative to help us decide what ways everything's moving. So we analyze the momentum in the X and Y direction. So first we're going to concentrate just in the X direction. We know that we have mass 1 initially moving in the X direction. We know that we have mass 2 sitting still, and afterwards we are going to have both masses moving, and we're just concentrating on the X direction. So looking at those, right, we have an 8 kilogram mass. It's moving to the right, so positive 15 meters per second. After the collision, in the X direction, right, this 8 kilogram mass, it's only moving south. So in the x direction, it's not moving. And so therefore, the 10 kilogram mass is moving in the x direction. So solving for our values, right, the final velocity in the x direction for object 2 is going to be a positive 12 meters per second. And so that means, right, we know it's moving to the east because it's a positive value. So now we're going to look at the y direction. So kind of working along the same line, right, of momentum's conserved, we're just focusing on the y direction. We can see that initially nothing was moving in the y direction. So because nothing was moving in the y direction, there was no momentum. We know afterwards that 8 kilogram ball was moving south, so negative 4 meters per second. And so we can figure out how fast the 10 kilogram ball is moving in the y direction. So solving for that, we get that the 10 kilogram mass is moving slower. It comes out to be positive, so it's moving at 3.2 meters per second. And because it's positive, we know it's moving in the north direction. So what we know now, right, we know that looking at our values, right, we know it's moving to the east and it's also moving to the north. So think back to projectiles. If we know the east and the north, right, if let's say we start the ball here where it was at rest, we know that is moving to the east at 12, it's moving to the north at 3.2, therefore this would represent the actual final velocity of that second object. So how can we find the magnitude of it? Well, it's a triangle, so a squared plus b squared equals c squared. So 12 squared plus 3.2 squared equals c squared. The magnitude of the velocity is 12.42 meters per second. So that is only part of our answer. That gives us how fast it's moving. It doesn't give us the direction. So we need to take it one step further and find the direction. So looking at our angle, right, we're looking for the angle that it came from to give us direction. So finding that angle, right, theta is the inverse of tan, right, and tan is opposite, so the opposite of that angle is 3.2. The adjacent to the angle, of course, is 12. And so punching that in your calculator, making sure you're in degrees mode, will give us that angle, and it comes out to be 14.93 degrees. So this line here is moving to the east, and our actual velocity is north of that, so the direction is 14.93 degrees north of east. You need both answers together in order to have your actual velocity for speed and direction. So hopefully this made sense, and we will work on those problems tomorrow.